Hello everyone, in this video we're going to be going through your OCR-A A-level chemistry paper 3, the paper that we've written for 2024. Now, there are a lot of skills involved in this paper, it's not just a knowledge dump, so please go and look at the exam skills, focus on how we've interpreted the question, how we can go through things and mark perfect.
This question is about the elements in period 3 of the periodic table. Here we're asked to give the full electronic structure of an atom of phosphorus. So the very first thing that I would do in this case is I would go to the periodic table to check how many electrons an atom of phosphorus has. So looking at phosphorus, I can see it's got 31.0 on the bottom and 15 on the top. I know that 15 on the top is the atomic number, which gives us the number of protons and therefore the number of electrons in an atom of that substance. So we need to get up to 15 electrons. So in this case then we're going to have 1s2 and then 2s2 and then we get 2p6 and then 3s2 and then 3p3. You can see there that those powers all add up to make 15 there, and that is the number of electrons in an atom of phosphorus. So now we're asked to define the term first ionisation energy. So this is another definition that we do need to know. It comes up very, very often. So if you don't know it, make a note of it now. Okay, so the first ionisation energy is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms. So in this question, 2 things are very important to include. We must include the reference to 1 mole of a substance. It's not just any number, it has to refer to 1 mole. We also need to refer to gaseous atoms. If this was in its solid form or something, no, that isn't the first ionisation energy, it has to be the gaseous form. So now we're asked to write the equation for the first ionisation energy of the element in period 3 with the lowest first ionisation energy. So the very first thing we need to do is which of these elements will have the lowest first ionisation energy? Well, we should remember that as we go across this period, we have the same number of shells, and therefore the shielding stays relatively the same. However, as we go across, the number of protons increases. Now this means that as we go across the period, we will get a greater attraction to those outer shell electrons and that more positive nucleus. As a result of this, sodium is going to be the element with the lowest first ionisation energy. And so we're going to use this to write our equation. So we've got Na, gaseous, is going to go to Na plus gaseous plus an electron. And the first ionisation energy would look similar for whichever element you have, you just replace the element. Okay, so now we need to identify the element whose ion forms a white precipitate with aqueous silver nitrate. We should be familiar with the fact that it is the chloride ion that will react with silver nitrate to form silver chloride, that white precipitate. Finally, now we're asked to identify the element with the smallest atomic radius. So what we need to think about here is a similar set of things as we did with the ionisation energy. As we go across this period, we're going to have the same number of shells. Therefore, there's no significant jumps in radius anywhere. However, we will have more protons as we move across this period. And as we have more protons, we're going to attract that outer shell towards the centre more. Now, the result of this is as we go across the period, we're going to get a smaller atomic radius. And therefore the element with the smallest atomic radius is argon. So now we're asked to explain why the melting point of silicon is 1414 degrees C, but for argon it's minus 189 degrees C. So whenever we're talking about melting points, we need to think about the bonding and structure within those substances. We should recognise that silicon has a giant covalent structure. However, argon, which is in group 0 or group 8, is a noble gas, and therefore it doesn't bond to anything. It's already got this full outer shell, and therefore argon is a monatomic gas, and that means it just exists as argon. Now, for that reason, we're not going to have any covalent bonds or anything we need to break. We're just going to need to overcome those intermolecular forces. So let's have a look at how we're going to turn this into our 3 marks in this question. So we need to start by stating that silicon forms a giant covalent lattice. So identifying that bonding and structure is going to get us our first mark. So our second mark is going to come from stating that argon exists as individual atoms, or by saying that it's monatomic due to its full outer shell. Next up, how we get our final mark is by concluding then that silicon has strong covalent bonds, which are going to require more energy to overcome than those weak London forces of attraction between the atoms of argon. So by making some level of comparison about the types of bond and their relative strengths, we're going to get our final mark in this question. Here I'm going the extra mile, and I'm just writing really clearly that silicon has strong covalent bonds, and it takes a large amount of energy to break these bonds, which gives it its high melting point. Whereas with argon, because it's monatomic, it only has London forces, which require only a little energy to overcome, and therefore it has a lower melting point. So there we have our perfect model answer that is going to come up time and time again. And do you know what? I always find people really struggle with these questions, even though it's only really using your AS knowledge. So make sure that you get your marks in these questions. They're quite often quite big mark questions. And if you didn't know any of this, then make some notes on it now, and then let's have a look at the next question. Stereoisomerism exists in both organic and inorganic substances, and the knowledge of this has been crucial in a wide range of applications, including medicine. Here we're asked to explain what is meant by the terms stereoisomer, cis-trans isomer, and optical isomer, using suitable examples from both transition metal and organic chemistry. Here we're asked to include diagrams in our answer. So let us get started here by defining stereoisomer. So we need to know that a stereoisomer is a set of compounds which have the same structural formula but have a different arrangement in space. So all of these isomer definitions involve the same something but a different something. And so a stereoisomer has the same structural formula but a different arrangement in space. So if you don't already know that definition, then get writing that down now. Okay, so next up we need to think about cis-trans isomers. So like it says here, these can occur in transition metal chemistry and organic chemistry. So when we have a cis-trans isomer, we need to know that cis means that we have 2 of the same group on the same side, and trans means that those groups are on different or opposite sides. So when we have a think about this in organic chemistry, we need to know that this occurs when we have a C-double-C bond. And the reason for that is that C-double-C bond restricts the rotation of those groups around the C-double-C bond. And that's how it differs to just an alkane. You know, that's why these alkenes are the group that sees this type of stereoisomerism. So let's have a go at drawing this here. Here I'm starting by drawing a cis isomer. You can see here that the 2 H's are on the same side. Whereas next I've drawn the trans isomer. Here I can see that those H's are on opposite sides. So to give that extra bit of information to make sure we get all of our marks in this 6 marker, we're going to say that this type of isomerism is caused in organic chemistry by restricted rotation around the C-double-C bond. So here we've got our examples, given our description. We can now have a look at cis-trans isomerism in transition metals. So there's a few different places where we can see this cis-trans isomerism. We can see it when we have the square planar version of the complex ions. Or we can also see it where we have bidentate or multidentate ligands as well. Now, in this case, I'm going to do my cisplatin. So here I have got cisplatin, which involves me having platinum in the middle, 2 ammonias on one side and 2 chlorines on the other. And now I'm going to do my transplatin, which has my Cls on diagonals, opposite sides, and my ammonias also on opposite sides, diagonal to each other. So that is just one example that we need to write. By all means, write down a different example if you prefer, but that's what I've got there. It's a nice, easy one to write down and to remember. So let's now have a think about optical isomers. So there's a little definition for optical isomers that we need to know. We need to know that optical isomers are non-superimposable mirror images of each other. It's quite a fancy sounding definition. All that means is that there's nothing you can do to twist and turn it to make it look identical to the other. The classic example is if you put both of your hands in front of each other, there's nothing that you could do to twist and turn your right hand to make it look the same as your left hand. They are actually mirror images of each other. So let's have a think about how optical isomers can pop up in organic chemistry. We need to know that the only time when we see optical isomers in organic chemistry is when we have a chiral centre. And generally speaking, that's going to be a carbon atom that has 4 different groups attached to it. So there's lots of different examples of this, including lots of the different alpha amino acids would fit this. However, I'm just going to make one up here. I've got my central carbon atom, I've got a tetrahedral structure, I've got chlorine on one bond, hydrogen on another, methyl on another, and bromine on another. I fit that criteria of that central carbon atom having 4 different groups attached. And I'm going to show the isomers by drawing this imaginary little dotted line, our mirror line, and I'm going to reflect this in that line. So the bromine is still the one nearest. Notice how the positioning of that bond is the same. We're going into the page for both of them. That also needs to get reflected, not just the atoms. So there we have it. I've got my organic isomers there that are optical isomers. Now let's have a look at how this might pop up in transition metals. Now, generally speaking, with transition metals, we're going to see that only when we have octahedral complexes and bidentate ligands surrounding it. So here we could give any real example of an octahedral complex with bidentate ligands. Here I'm going to use the ethane diamine ligand. And for illustrative purposes here, I'm going to use the common notation of just En to represent that. So the first thing I do when drawing an octahedral complex is I put my metal ion in the middle and then I do the shape around it, because so long as the shape looks right, then we're doing well. So I do my stick up and down, my 2 into the page and my 2 out of the page. So now, like I mentioned, I'm going to choose ethane diamine, but I'm going to represent that with the En notation. So I'm going to join 2 of these bonds, another 2 and another 2. I'm then going to put my square brackets around this. I'm going to put a little 2+ up for the charge of the ion. The ethane diamine ligand doesn't have a charge. Then again, I do my mirror line. I will always draw the structure of the bonds first, and then I'm going to show that reflection of those bonds. So I've got this mirror image of those bonds, and you can see that they're taking a different position here. So I'm still going to put the square brackets around this because complex ions generally have them, little 2+ up there. And then I'm just going to make a little note that the En represented that ethane diamine ligand. You could, of course, have drawn that. I just didn't because I didn't want it to look really unclear for you. But if you do bond that on, make sure that the nitrogens are the bits attached to the bonds, because they are the parts of that ligand that are donating their lone pair of electrons to form the coordinate bonds. And so there you have it. Those are all of the things that we need to say to get our full marks in this question. Remember, in these 6-mark questions, we're not getting assessed by saying 6 points. We need to make sure that we give a well-developed answer, which gives thorough explanations of the stereoisomer, cis-trans isomers, and optical isomers for both the transition metal and organic chemistry. If we leave out a section of that, then we're going to massively limit the amount of marks that we get, and potentially would only get 1 or 2 marks if we only gave, say, organic examples. So, I hope that made sense. If you didn't remember these things, then do make some notes on them now. Thin layer chromatography is commonly used in the identification of organic substances. However, with the right selection of solvent and surfactants, the process can be used to identify inorganic metal ions. The chromatogram below was made using an unknown sample and some metal ions. Using the chromatogram, identify the metal ion present in the unknown sample. So what we need to do is to look at that sample spot and read along to see which one it matches. Here I can see the only one it matches with is the copper 2+ ion. So that is our answer. Here we're asked to calculate the RF value of Fe3+. So to do this, let's first remind ourselves of the formula. So the RF value is calculated by taking the distance moved by our substance, in this case the Fe3+, from that baseline, and then the distance moved for the solvent. So that is going to be measured between the baseline and the solvent front. So now what we need to do is we need to get our rulers out, okay? And it doesn't matter where we're measuring this, whether it's on a printed out page, on the screen, whatever, the ratio will be the same. So I make it on my screen it to be a distance of 1.3 centimetres moved by the Fe3+. And now we need to divide that by the distance moved by the solvent. And we're going to measure the distance between the baseline and the solvent front. And that is 6.1 centimetres in this case. You will probably get different numbers, but your RF value should still be the same. So here we've got RF equals 1.3 divided by 6.1. And that ends up giving me an RF value of 0.21. So now we're told that transition elements can also be identified by their colour. Here we're asked to state the colour of the Fe3+ ion in solution. So we should know that the Fe3+ ion is yellow in colour. So now we're told that aqueous 3+ ions react with iodide ions as shown in the equation below. Here we're asked to explain the meaning of oxidation and reduction in terms of electrons and to identify the substance that's reduced and the substance that's oxidised. So we should remember here that reduction involves the gain of electrons, whereas oxidation involves the loss of electrons. And the little memory prompt that we often use there is oil rig. Oxidation is loss of electrons, whereas reduction is gain of electrons. So here we're asked to identify the substance that gets reduced and the substance that gets oxidised. Let's have a look at what changes here. I can see that the Fe3+ goes to Fe2+. Now in going from 3+ to 2+, it's become a bit less positive. That must mean it's gained a negative thing, an electron, and therefore the Fe3+ must have been reduced to the Fe2+. Whereas the I- going to I2, it's lost its negativity. So it must have lost the electrons, and therefore I- has been oxidised to I2. Another method for the identification of transition metals is gas chromatography. Here we're asked to describe how gas chromatography can separate substances in a mixture. So this here is quite a common question, just testing our understanding of how gas chromatography works. So we should know that gas chromatography separates substances based on the solubility of that substance. So there we are. If you didn't know that, then make a little note of it, so that then if it comes up again in your exam, you get that mark. Fizzy drinks are made from a variety of ingredients, often including carbonated water, caffeine, sweeteners, flavonours, preservatives and colouring. One of the sweeteners regularly used in these drinks is aspartame, which is shown in the diagram below. Determine how many chiral centres there are in this molecule and label these with a star. So we need to remember that a chiral centre has 4 different groups attached to it. So we're looking for a carbon atom that has 4 different groups attached. Now, as soon as we have a double bond or something, that's going to prevent us having 4 different groups. That will also apply within benzene as well, because we only attach to 3 different atoms for each carbon atom. So let's run through these one by one and decide if they are chiral or not. So this first carbon isn't, because it's got the C to O double bond. Next up, looking at this next carbon, I can see it has 2 hydrogens attached. Be very careful of skeletal formula, that's what throw people on this topic. So the next carbon has an H above and an NH2 below, and to each side it has different groups. So that is a chiral carbon. The next one has a double bond again, so it can't be. This next carbon over here does have 4 different groups attached, so that one is also chiral. This next carbon up here has 2 hydrogens, so that one can't be chiral. Next up, let's look at the benzene. All of these carbons only have 3 atoms bonded to them, so that doesn't work either. This next carbon has a double bond, so it can't be. And finally, this carbon on the end, it actually has 3 hydrogens bonded to it. So as a result of that, that is not a chiral carbon. So we've only got 2, so we're going to put stars on the diagram in the relevant places. And there we have it. There are our 2 marks. One of the functional groups in aspartame is an ester. Identify the other functional groups present. So highlighting here, I can see that I have a carboxylic acid. I have that COOH group. So that is one of our functional groups. Next up, I have an NH2. Now I know that that is an amine group. So that is my second functional group. And we have one more here, and this is one that gets missed by many or gets confused with other things such as ketones. We have an amide bond here, because we've got the C double bond O attached to an NH. So those are our 3 different functional groups present that we need to talk about. Carbonated water is what makes the drink fizzy. When carbon dioxide is added, an equilibrium forms between the CO2 and water, and a weak acid called carbonic acid, as shown in the equation below. Here we're told that a 335 milliliter can of cola has a carbonic acid concentration of 0.15 moles per decimeter cubed. A hiker took the can to the top of Mount Everest, where the pressure was 34 kilopascals and the temperature was minus 20 degrees C. Assuming the carbonic acid fully dissociated, calculate the volume of carbon dioxide in decimeter cubed that was released upon opening the can. So we've got a really interesting question here. Let's have a think about what information we know. We know the volume of this can, and we know that it's 335 millilitres. We should know that that is the same as 335 centimetres cubed. That's a really important relationship we know. So we also know that the concentration of this can of cola is 0.15 moles per decimetre cubed. We can therefore work out the moles of the carbonic acid in this can of cola by doing concentration times volume over 1000. So putting the numbers in, we have 0.15 times by 335 over 1000. Now putting that into the calculator, I get 0.05025 moles of carbonic acid. And that is our first important step of our calculations. So this question is asking about the carbon dioxide. Now looking at this balanced equation here, I can see that there's a 1-to-1 ratio between carbonic acid and carbon dioxide. Therefore, we can say that we also have 0.05025 moles of carbon dioxide. So there we have it. We have information now to work out the volume of carbon dioxide. Now, because it's a gas, we're going to use PV equals nRT. Let's look at what we know the temperature and the pressure are in this question. So we're told that the temperature equals minus 20 degrees C. However, we should know that in this formula we must use Kelvin. So we add 273 to this and get the temperature to be 253 Kelvin. Next up, let's look at the pressure. Pressure needs to be in pascals, and this is 34 kilopascals. So to convert this to pascals, all we need to do is to multiply through by 1000. That gives us 34,000 pascals. So now we have enough to substitute some numbers in. Here we have 0.05025 times by 8.314 times by 253, and we divide it by 34,000. So popping this into the calculator is going to give us the volume in meters cubed. So here I get 3.10876 times 10 to the minus 3 meters cubed. However, the question, as you can see, wants it in decimeter cubed. Always go back after getting an answer to check that final little bit of information that they may have asked for. So to convert from meters cubed to decimeter cubed, all I need to do is multiply through by 1000. That gives us 3.1 decimeters cubed for our volume of carbon dioxide. It's been found that refrigerating cola keeps it fizzy for longer. Using Le Chatelier's principle, explain this observation. So first things first, let's just remind ourselves of the balanced equation. Okay, so I'm just going to scribble it down here. So the equation states that CO2 plus water goes to this carbonic acid. We also know delta H, the enthalpy change, is 2.2 kilojoules per mole. So this enthalpy change is going to be important because in this question we're talking about refrigerating the cola and therefore decreasing the temperature. Well, when we have a positive enthalpy change, that means that the forward reaction is endothermic and therefore the backward reaction will be exothermic. While thinking about Le Chatelier's principle, if we decrease the temperature, the equilibrium will want to shift into the exothermic direction to increase the temperature again. Therefore, what this is going to cause to happen in this particular reaction is it's going to lead to more carbon dioxide and water being produced. Now, if we think about what the question wants, why is it that refrigerating it keeps it fizzy for longer? Well, it's because more fizz is going to be caused by more bubbles. And more carbon dioxide, therefore, will make it more fizzy. And so here we get our 3 marks, firstly for stating that the equilibrium will shift to the exothermic side, then for expressing the fact that we're going to get more carbon dioxide and more water, and then making it clear that more gas molecules means more fizz. The weak acid benzoic acid is found in many fizzy drinks as it's used as a preservative. Here we're asked to construct an equation for the dissociation of benzoic acid into its ions in water, and here we're asked to include state symbols. So they've already given us the formula, it's C6H5COOH, and that's aqueous. We need to use the reversible symbol here because it's a weak acid, and it dissociates into C6H5COO- aqueous, because it loses and dissociates its H+, and then plus that H+, which is also aqueous. So all of the state symbols in this question need to be AQ for aqueous, and we need to make sure that we have that reversible symbol in the middle there to get our mark. A bottle of cola contains 6.5 times 10 to the minus 4 moles per decimeter cubed of benzoic acid at 25 degrees C. The acid dissociation constant at this temperature, Ka, was found to be 6.3 times 10 to the minus 5 moles per decimeter cubed. Here we're asked to calculate the pH of benzoic acid in the bottle of cola and give your answer to 2 significant figures. So we should recognise here, and it was mentioned earlier, that benzoic acid is a weak acid. The formula for benzoic acid is C6H5COOH, and when it dissociates we use this reversible symbol and it becomes H plus C6H5COO-. Now the reason why that dissociation equation is so important is because it will help us write this equation for Ka. So we know that Ka equals the concentration of H plus the concentration of C6H5COO- over the concentration of this benzoic acid. Now, an important thing to know here is because we just have a solution of benzoic acid here, we can approximate the concentration of the H plus ion with that of the C6H5COO- ion, and say that they're about the same. And really importantly there, that enables us to rewrite this then as Ka equals the concentration of H plus squared over the concentration of benzoic acid. And that's really important because that removes a whole variable. So we know the concentration of benzoic acid is 6.5 times 10 to the minus 4. And we also know that the value of Ka is 6.3 times 10 to the minus 5. So now that we know this, we can rearrange this equation to find out what the concentration of H plus is. And that's all thanks to that nice little approximation that we could make earlier. So if I rearrange this, I get that the concentration of H plus equals the square root of Ka times by the concentration of benzoic acid. So if I put the numbers in there then, I get that the concentration of H plus equals the square root of 6.3 times 10 to the minus 5 times by 6.5 times 10 to the minus 4. So popping that into the calculator, I end up getting an H plus concentration of 2.0236 times 10 to the minus 4. And the great thing is that once we know that H plus concentration, we can get that pH equals minus log H plus. This is such an important equation, you have to know it. So if we substitute our H plus concentration in, we get that pH equals minus log of 2.0236 times 10 to the minus 4. Putting that into the calculator, I get 3.69387539, and if I check back earlier into the question, I can see I need to give my answer to two significant figures. So rounding this up then, I get 3.7 for my pH of benzoic acid. A food scientist wanted to determine the concentration of the weak acid citric acid in a 2-litre bottle of a fruit-flavoured drink. They boiled the drink to make it more concentrated until there was a volume of 500 centimetre cubed. They then titrated 20 centimetre cubed of this concentrated solution against 0.02 moles per decimetre cubed of sodium hydroxide. This sodium hydroxide was added incrementally from a burette. They used a pH meter to determine the pH after each addition of sodium hydroxide. The equation for the reaction of citric acid with sodium hydroxide is as given below. As you can see, I'm not going to say that out loud, it's a big equation. And the results are shown in the graph below. And so next up, we're going to be asked some questions about all this information we've been given here. Using the graph, determine the concentration of the citric acid in the original 2-litre bottle. And here we're assuming that citric acid is the only acid present in the drink. So the first thing we need to do here is to have a look at the equivalence point, so the point where this vertical region is. I can see that corresponds to 10 centimetres cubed of sodium hydroxide being added. So paired with the fact that we're told that the concentration of sodium hydroxide is 0.02 moles per decimetre cubed, we can work out the number of moles of sodium hydroxide that were added here. So we know that moles is equal to concentration times volume, and as the units are inconsistent, it's over 1,000. So in this particular question here then, we've got the moles of sodium hydroxide is equal to 0.02 times by 10 for that volume over 1,000, and that gives us 2 times 10 to the minus 4 moles of sodium hydroxide. So now we need to have a look at that balanced equation from the previous page. I can see that between the citric acid and the sodium hydroxide, I've got a 3-to-1 ratio. So I've got 3 times less citric acid than I do sodium hydroxide. So therefore I can work out the number of moles of citric acid by taking 2 times 10 to the minus 4 and simply dividing it by 3. Now that gives me 6.67 times 10 to the minus 5 moles of the citric acid. So for this question, we're being asked to determine the concentration of the citric acid in the original 2-litre bottle. So we need to know that those moles of citric acid was corresponding to the 20 centimetre cubed of it that we titrated. However, that 20 centimetre cubed was just a small sample of the 500 centimetre cubed of drink we had earlier. So we need to work out, well, if there's 6.6 to the 7 times 10 to the minus 5 moles of citric acid in 20 centimetre cubed of this drink, how much will there be in 500 centimetre cubed? And so we need to multiply that number by 25. And that will give us the moles of citric acid in that 500 centimetre cubes of drink. So that gives me 1.6675 times 10 to the minus 3 moles of citric acid. So finally here, we're being asked for the concentration of citric acid in the original 2-litre bottle. Well, of course, we've just been talking about 500 centimetres cubed of this drink. However, remember that it started as 2 litres, but then we heated it up until eventually it got more concentrated and we had that 500 centimetre cubed solution. And what we need to understand here, though, is in that process of heating it and removing some of the water, the number of moles of citric acid hasn't changed. Just the concentration of it has changed. So when we're trying to work out the concentration of this original 2-litre drink, we need to still use the same number of moles. However, we're going to use the volume of 2 litres, which is actually a volume of 200 centimetres cubed. So that's what we need to use there. So let's have a look at this then, okay? Here we're going to have concentration equals 1.6675 times 10 to the minus 3 divided by 2,000, because that's how many centimetres cubed in 2 litres. And then we times by 1,000 to change that unit from the centimetres cubed to the moles per decimetre cubed we need for the concentration. So, putting this into the calculator, I end up finding that I have a concentration of citric acid of 8.3 times 10 to the minus 4 moles per decimetre cubed. And so that there is our answer to this part of the question. Here we're asked to calculate the Ka value for the citric acid used in the titration of the fruit flavoured drink. And we're asked to give your answer in standard form to 2 decimal places. So to do this, we need to know the fact that the pH at the endpoint is the same as the pKa value of this acid. And so if we look here at this curve and we look at this vertical region, we look at the bottom of the vertical region and the top of the vertical region, and we look at the pH bang in the middle. That is going to be the pH of the endpoint. And therefore, due to that statement that we said, at the endpoint, the pH is the same as the pKa. So therefore we can deduce that the pKa is also equal to this 8.5. Now we know that Ka is given by 10 to the minus pKa. And so in this case, Ka will equal 10 to the minus 8.5. This ends up giving me, to 2 decimal places and in standard form, 3.16 times 10 to the minus 9. And there you have it, that's your answer. On the graph in part E, sketch how you would expect it to change if 0.01 moles per decimetre cubed of sodium hydroxide was used instead. So the fact we need to use here from earlier is that previously we used a concentration of sodium hydroxide of 0.02 moles per decimetre cubed. So by changing to 0.01, we've essentially halved the number of moles of sodium hydroxide that we have in this scenario. So because of that, if we've halved the concentration and therefore the moles in this system, we're going to have to add double the amount of sodium hydroxide to do the same thing. So therefore what we're going to do is we're going to shift this vertical region from 10 to 20. Everything else is going to stay the same. We're going to start it at the same point and end it at the same point, but the position of that vertical region has now been moved to 20. So now, using the table below, suggest the name of a suitable indicator that the food scientist could use for the titration instead of using a pH meter. And we want to give a reason for your choice. So what we need to do here is to look at this vertical region. And we want to look at the bit where it's purely vertical, not where there's any curvature of that line. And we want to find the pH range that is contained within that vertical region. And here, out of all of these, I can see that the only one that does is going to be the metacresol purple. And so our reasoning for this is that the vertical section occurs between this 7.4 and 9.0 pH range. And so that's how we choose our answer. Ozone has a vital role in our atmosphere, absorbing ultraviolet radiation. The bonding in ozone is shown below. Ozone has 2 sigma bonds and 1 pi bond. Here we're asked to draw a diagram to show how the pi bond forms in ozone. So let's have a go at sketching out this bonding, okay? So the pi bond is going to be where this double bond is. So first we'll do a single bond between, which represents that sigma bond that it has. But then we're going to show the p orbitals, which are dumbbell-shaped orbitals above and below the bond. Now these orbitals overlap. It's very, very hard to represent this fully. That's where I've done this sort of shaded region between them. But it's that overlapping of the p orbitals that forms our pi bond. So what I'm going to do now is I'm going to draw this region above and below that bond to show our pi bond. So before I finish this question, I'm going to make sure I label it. I'm going to label on my p orbitals, and I'm also going to label on my pi bond. So there we have it. That is something that we can extend to many other examples. It's not just going to be for ethene or something. Like you can see, we could do it for an unknown molecule here, like ozone as well. So make sure you get learning this general diagram to show the formation of a pi bond. So one example of a CFC is chlorotrifluoromethane, which can form chlorine radicals in the presence of ultraviolet light. Here we're asked for a really, really standard definition that we need to know inside out. We're asked to state what's meant by the term radical. So we need to know that a radical is a species with an unpaired electron. That definition is just so common, there's no way that we can go into this exam without knowing it. So if you don't know it now, make a note of it or a flashcard right now and make sure that by the end of the day you know it. So now we're asked to write the equations which show how the formation of chlorine radicals from CF3Cl in the presence of ultraviolet light can deplete ozone in the stratosphere. So first up here, we need to write an initiation step. And we're looking at the formation of chlorine radicals from CF3Cl. So we need to have the CF3Cl, and with an arrow with ultraviolet light above it, we're going to crack it into, using homolytic bond fission, into CF3 radicals and Cl radicals. So now with the propagation step, we're going to take one of those radicals, so the chlorine radicals that the question talks about, and we're going to deplete the ozone. So remember, ozone has the formula O3. So because this is a propagation step, on the reactant side, you're going to have one radical, and on the product side, you're going to make a new radical. So what we're going to see here is that ozone is going to break down into an oxygen and an O, where the O is going to go towards that Cl radical. And that's what makes this ClO radical, leaving us with just an O2 as our other product. So propagation steps always come in twos. So that ClO radical is now going to propagate into the second step. So we're going to have the ClO radical is going to react with oxygen in the atmosphere, just O. And what is going to happen here is that the oxygen from the ClO radical is going to break apart and bond with the oxygen atom. And that leaves us then with just the Cl radical and oxygen O2. Now this is actually a really, really common process. So here in this case, these propagation steps, we can actually just go away and learn them as examples of this depletion of the ozone in the atmosphere. So finally here, we're asked for an overall equation here. So if we look at these two propagation steps, we can see that we've got radicals on each side of both the Cl radical and the ClO radical, and these can just cancel out. Now, that means then that on the reactant side, we're just left with O3 plus O, And over on the product side, you can see that we're left with 2 oxygens. And so that leaves us with 2 O2 on our product side. And we can clearly see that that balances. We have 4 O's on the reactant side and 4 O's on the product side. So there we are, that is our overall equation. And I would always recommend, whenever you need an overall equation, you just imagine like an imaginary line where the arrows are, and you just see, is there anything that is on both the reactant side and the product side? And you'll just cancel those through, like I did here with the Cl radicals and the ClO radicals, and we just mush together all of the things that are remaining there. And so there we have it. We've written the equations which show how the formation of chlorine radicals in the presence of UV light can deplete ozone in the stratosphere. Ozone is also involved in the breakdown of alkenes to form carbonyls. This is called ozonolysis. These carbonyls are then treated with the sulfur ylides to form a special group of cyclic compounds called epoxides. Epoxides can also be made from alkenes in an alternative 2-step synthesis. Epoxides are used in large quantities by the chemical industry due to their extremely high reactivity. The diagram below shows the formation of an epoxide called 2,3-butylene oxide from buteene by these 2 different routes. Ozonolysis of buteene forms 2 molecules of the carbonyl E as shown by reaction 1. And I've just drawn reaction 1 to the side here so we can reference it. Here we're asked to draw the displayed formula of this substance E that gets made. So here we need to remember this is ozonolysis. Lysis means that we're breaking apart the bond using this ozone. And so we need to imagine we're breaking apart this double bond using the ozone. Now we also know we're forming a carbonyl. So I think it makes sense to imagine that we form this carbonyl bond, and then we still have that CH3 and the H. So as you can see here, if this was the carbon, we have the H is still in the same position, and the CH3 is still in the same position, but all that's happened is we've broken apart that double bond and replaced it with an oxygen. You can see here we get 2 substance E's. We know we used O3 and we made a spare oxygen. So it makes quite a lot of sense, I think, that 1 oxygen goes to each of those 2 carbonyls and then you're left with a remainder, okay? So here, this is what I have gone with here. The displayed formula of substance E is that of ethanol. Okay, so next up we're asked to give the IUPAC name of substance F. So I've put F over here on the right hand side so we can look at it. So first things first, let's work out how many carbons are in the longest chain. I can see that the longest chain is 4 carbons, so we're going to have a bute in the name. I'm going to number it now, and I'm going to make sure that the alcohol has the lowest number possible, because that alcohol is the main functional group that we have here. So by numbering in this way, we can see that we have a bromine on the 3rd carbon, so we've got 3 bromo, and because we have this alcohol group, we've got butan 2-ol. So the 2 is representing the position of that alcohol. And so in total here we have 3 bromo butan 2-ol. So I hope that made a lot of sense how we named that. So next up we're asked to name the mechanism that forms substance F from buteene via reaction 3. So if we have buteene and then we end up breaking that double bond of the alkene and forming substance F, we need to know that we have electrophilic addition. And we will always have electrophilic addition where the mechanism involves taking a double bond, a CC double bond, and breaking it apart to just form single bonds between those carbons. Okay, so electrophilic addition is the name of that mechanism. Below is a partially completed mechanism for the formation of 2,3-butylene oxide from substance F, as shown by reaction 4. Here we're asked to complete the mechanism by including appropriate dipoles and curly arrows. So whenever I have a mechanism question like this, and it's an unknown one, and I need to complete in some information myself, add in the curly arrows and everything, I like to play a little bit of spot the difference between the different steps. So here, if we take the first step, this one, and the second step, and just see what's changed, basically, going from one to the other, I can see that I no longer have this hydrogen attached anymore to the oxygen here. I can see instead I have O-, which means it's gained a pair of electrons, I can see by comparing the two. So for that reason, I know that I'm going to need a curly arrow to show the breaking of that bond and the movement of the electrons to that oxygen. So that's the very first thing that I do. I move the pair of electrons from that bond to the oxygen. Now it's gained that lone pair. And I'm also going to draw in the dipole that I know exists between that carbon and the bromine, because I know bromine is more electronegative than carbon. And I'm going to fill that in on the second step too. So now I've done everything I can on that first step. I'm now going to compare the second and the third step, that final step. And again, I want to play a little bit of spot the difference. I can see that here I have this carbon to bromine bond. I can see that it isn't present in this final step. Instead, the bromine has broken away and it is now just a bromide ion, okay? I can also see that I have formed a brand new bond. I can see that I have that oxygen, which is here, is now bonded to this carbon. Now that must mean that some of the electrons from that oxygen have moved to the carbon to form a covalent bond. So now that we've had a think by playing the spot the difference, let's have a go at putting those curly arrows into action and showing us breaking that bond between the carbon and the bromine, and show us making a bond between the oxygen and the carbon. So first things first, let's move a pair of electrons from that O- to the carbon, and then let's move the electrons from the carbon to bromine bond, from the bond to that delta negative bromine. So by doing that now, we have broken the bond between the carbon and the bromine, and we now have that bromide ion, and we have made the bond between the carbon and the oxygen. And there we have it. There is our completed mechanism, one that we'd never seen before, but we didn't panic. We just used the fact that curly arrows show the movement of a pair of electrons. We drew in our dipoles, and we played a little game of spot the difference, so we knew what the aim of the game had to be. We needed to know what each step needed to represent, and we could do that just by comparing the first step with the second, and then the second step with the third. So now we're asked to describe what a curly arrow in a mechanism represents. Well, I've just mentioned it, and of course we've been using that fact throughout this mechanism question. It is the movement of a pair of electrons. Don't just say the movement of electrons, that won't get you your mark. Make sure you say it's the movement of a pair of electrons, and make sure that you do not go into the exam without knowing that fact. A chemist wanted to form a carbonyl G from substance F. The molecular formula for G is C4H7OBr, and the yield for this reaction is 76%. Here we're asked to describe a method that the chemist could carry out to produce 15.0 grams of G from F. And your response should include a labelled diagram of the apparatus used, reagents required, and the relevant equations and calculations. Now do notice that this question has that little star in the corner. And what that tells us is that we don't just get 6 marks for saying 6 things. We need to give a full, well-developed answer that includes all of the things they asked for. So this apparatus, the method, the reagents, and all these equations and calculations. All of it needs to be included to get our 6 marks. And it all has to be in a logical, coherent form. So let's get started here with describing our method and all of the apparatus that we need to be able to carry out this experiment. Okay, so the first thing I want us to do is just remind ourselves of what substance F was. So you may remember from earlier that substance F was 3-bromobutane-2-ol. Now we're using that to form a carbonyl. We should know that as 3-bromobutane-2-ol is a secondary alcohol, the carbonyl we're making is a ketone. So we can write a relevant little equation here that states that we have F, which is C4H9OBr, plus O in our little oxidizing agent brackets, makes C4H7OBr, that carbonyl G, plus water. And because we took the time to write down that equation that we need, we now know what method we're looking for, okay? We know that we need the method that's going to take us from a secondary alcohol to a ketone. So like we said, in these little starred questions, we want to give a very, very thorough explanation here. So the first thing we would want to do is to measure the mass of F on a balance. Once we've done this, we're going to add some anti-bumping granules. Now make sure that you know the purpose of anti-bumping granules, because they could ask you that as well. The whole point of them is they enable the liquid to boil more calmly. So there's not going to be any splashing as it boils. It's going to stay nice and a smooth boil. Okay, so now on to our third point here. Now we want to add acidified potassium dichromate, which is our oxidizing agent in this experiment. So we're going to put all of this into a round or a pear-shaped flask, which has a condenser in an upright position. Now the point of this experimental setup is that it's going to enable us to carry out reflux. And we need to know that it's reflux that we need to do to be able to make a ketone from a secondary alcohol. So the next thing we need to do is we need to heat this. We're going to heat it using something such as a heating mantle or a water bath. And we're just going to gently heat it to a point just above its boiling point. So, of course, here our oxidizing agent was acidified potassium dichromate. What we're going to observe when the reaction is complete is a colour change from orange, which is the original colour of the potassium dichromate, to green. And that's how we're going to know that the reaction has completed. And the final step that we can use right at the end here is going to be that purification step. So we're going to need to finally distill this solution at a boiling point of G. So the boiling point of G is of course the boiling point of our carbonyl. Of course we made water here as well, and that's why we need to distill this, so that we can remove G from the water and we just have pure ketone. So this question requires us to include diagrams to get those full marks. So let's make sure we do that. So here I have a heating mantle that I'm drawing, and I'm going to place a round bottom flask above that heating mantle. Within that round bottom flask, I'm going to include my substance F and those anti-bumping granules, and of course my acidified potassium dichromate as well. So here I'm drawing some little dots to represent those anti-bumping granules. Here I've also got this upright condenser. Now a really important part of our diagram here is that we show that the water goes in at the bottom of our condenser and it leaves at the top of the condenser. Now make sure that you do include that. Now of course our diagram, if it's really well labelled, can sort of be taken as some of the points from our description of our method. So they can support each other, but do make sure that you give as full an answer as possible, and make sure that you fully label this diagram of the apparatus as well. So there we have it, there is our diagram. And so we've described all of our method, we've got our diagram, we've got our apparatus. We want to finish up now with some calculations to show exactly how we can produce 15 grams of G from F. Okay, so we're still on the same question. It is certainly going on a bit, but now we need to do the maths to show how we can produce 15 grams of G from F. So what we need to think is, because this is just a yield of 76%, we need to work out, well, how much F do we actually need? Let's remind ourselves of this balanced equation. And the reason why a balanced equation is always important is because of that all-important molar ratio. And here I can see that the molar ratio between our alcohol and our ketone is 1:1. So actually it's fine. we can work out the amount of moles that we're going to need to make of our ketone to work out how many moles we need of the alcohol to make that ketone, okay? So, first things first, we know that the mass of G that we're going to aim to make is 15 grams. So we know that the MR of G, so the MR of C4H7OBr, is going to be equal to 4 times 12 plus 7 times 1 plus 16 plus 79.9. And that gives us an MR of 150.9. So now we know that we're aiming to make a mass of 15 grams, and we know the MR, we can say that the moles of C4H7OBr is equal to mass over MR, which is 15 over 150.9. And that gives us 0.0994. Now, thanks to the fact that, of course, we have this 1-to-1 ratio, this is also the number of moles that we need for substance F. So 0.0994 is the theoretical number of moles needed to carry out this reaction and to produce 15 grams of G. So because it's a 76% yield though, we need to work out what we actually need. So if we have 0.0994 and if we divide it by 76 to work out what 1% is, and then times by 100 to see what that 100% is, how much do we actually need, then we get 0.1308 moles. And that's the number of moles that we actually need to make those 15 grams of G. So now that we know the actual number of moles that we need, we can work out what mass of the alcohol of substance F we're going to need. And quite simply, the way we'll do that is mass equals MR times moles, which means we need the MR. And the MR of this substance is 152.9. So by using the equation that mass is equal to Mr. moles, MR times by the moles, we end up getting 152.9 for the MR, times by those moles of 0.1308. And popping that into the calculator and rounding it to one decimal place, I get 20.0 grams. The question hasn't said how much we round it to, so we could give the whole calculator value or we could round to more decimal places, all will be fine. But here I've got 20.0 grams as my mass of F. And so in our method, that is the amount that we need to measure out of F to then go on and reflux to be able to make G. So there we have it. There is that question done. It was a biggie. Make sure that you understand why we included everything we did, but that's what we need to say to get our full 6 marks in this question. So here we're asked to describe a test to distinguish between carbonyls E and G. So remember, E is an aldehyde and G is a ketone. So we need to think, what test do we have that distinguishes between aldehydes and ketones? And the test that I'm going with here is Tollene's reagent. Now, Tollene's reagent will form a silver mirror when we have an aldehyde present. However, when we have a ketone present, we have no change. We have no silver mirror formed. And so here, this is a 3-mark question. We're going to get 1 mark for stating Tollene's reagent. We're going to get 1 mark for explaining that when we react it with E, our aldehyde, we're going to form a silver mirror. And we'll get our 3rd and final mark for stating that when we react Tollene's reagent with G, our ketone, we observe no change and we have no silver mirror.
Ouch! This is why in some videos I explain scratches.